NASA just confirmed something about Voyager 1 that its own engineers are struggling to explain, and the timing could not be stranger. The most distant human-made object in existence, a machine older than most of the people currently monitoring it, appears to have detected something that should not be possible given everything we know about the region of space it's currently traveling through. Voyager 1 launched in 1977, and for nearly 50 years, it has done exactly what it was built to do: travel outward, take readings, and send them home. It is currently more than 25 billion kilometers from Earth, a distance so vast that a single radio signal moving at the speed of light takes almost 24 hours just to reach it. Later this year, Voyager 1 is expected to cross an unprecedented threshold, becoming the first human-made object to sit a full light day away from the planet that built it. That milestone alone would have been the biggest Voyager story of the year. Then, weeks before it happened, something else took over the conversation entirely. Voyager 1 has never been an ordinary spacecraft, even by the standards of NASA's most celebrated missions. It was the probe that gave us our first close-up images of Jupiter's turbulent storms and discovered active volcanoes on the moon, Io, the first confirmed volcanic activity found anywhere beyond Earth. It captured Saturn's rings in a level of detail nobody had ever seen before, and in 1990, on its way out of the solar system, it turned its camera backward at the request of astronomer Carl Sagan and photographed Earth from nearly 6 billion kilometers away, producing the image now known as the pale blue dot. In 2012, Voyager 1 became the first human-made object to officially cross the heliopause and enter true interstellar space, a boundary scientists had theorized about for decades, but never actually measured directly until Voyager 1 passed through it. Every one of those milestones came with careful, predictable, well-explained science behind it. This is the first time in the mission's history that the explanation isn't coming easily. To understand why this new development has caught even veteran engineers off guard, you need to understand just how fragile Voyager 1's continued existence actually is right now. Both Voyager probes run on radioisotope thermoelectric generators, power sources, that convert the heat from decaying plutonium into usable electricity. That power has been draining at a steady, well-documented rate of about 4 watts per year since the mission began. A slow bleed that NASA has spent decades managing by shutting down instruments one by one to keep the spacecraft alive. In April of this year, engineers made the difficult decision to power down Voyager 1's low-energy charged particles instrument, a device that had operated almost continuously since launch, measuring cosmic rays and charged particles from our solar system and beyond. It was a sacrifice, made specifically to buy time for an upgrade, nicknamed internally as the Big Bang Fix, an attempt to squeeze a little more operational life out of a spacecraft that everyone involved knows is approaching the end of its road. It was during preparation for that very fix, while engineers were combing through Voyager 1's remaining instrument data more closely than they had in years, that something unusual surfaced. If you're new to this channel, we cover stories exactly like this one every week, so hit subscribe now before we get into what NASA is calling one of the strangest readings in the mission's entire history. According to details that have circulated among mission scientists in recent days, the anomaly first appeared in data from Voyager 1's magnetometer, one of the few instruments still functioning on the aging spacecraft. The magnetometer exists to measure magnetic fields, and out in interstellar space, far beyond the protective bubble of our sun's influence, those fields are expected to behave in a fairly predictable, well-mapped way. Voyager 1 crossed into interstellar space years ago, and since then its magnetic field readings have followed a consistent pattern that matched theoretical models built up over decades of research. That consistency is precisely what makes the newest data so difficult to explain. Engineers reviewing the recent telemetry noticed a magnetic field fluctuation unlike anything recorded before, not just in strength, but in structure. Instead of the smooth, gradually shifting readings typical of interstellar plasma, the data showed a sharp, localized spike that appeared and then vanished within a window of just under 6 minutes. Fluctuations do happen out there, caused by solar activity reaching further than expected, or by the turbulent boundary where our solar wind collides with the interstellar medium. But those fluctuations typically build and fade gradually, over hours or days, not appear and disappear in minutes with almost surgical precision. Engineers reviewing the recent telemetry noticed a magnetic field fluctuation unlike anything recorded before, not just in strength, but in structure. Instead of the smooth, gradually shifting readings typical of interstellar plasma, the data showed a sharp, localized spike that appeared and then vanished within a window of just under 6 minutes. Fluctuations do happen out there, caused by solar activity reaching further than expected, or by the turbulent boundary where our solar wind collides with the interstellar medium. But those fluctuations typically build and fade gradually, over hours or days, not appear and disappear in minutes, with almost surgical precision. It helps to understand what Voyager 1's magnetometer is actually built to do. and why its readings are normally so trustworthy. The instrument measures the strength and direction of magnetic fields using two sensors mounted on a long boom extending away from the spacecraft's main body, specifically positioned to avoid interference from Voyager 1's own onboard electronics. It was the same instrument that confirmed Voyager 1's historic crossing into interstellar space back in 2012, detecting the telltale shift in magnetic field orientation that told scientists the spacecraft had finally left the sun's protective bubble behind for good. An instrument with that kind of proven track record, still returning clean, interpretable data after nearly 50 years, is not something engineers dismiss lightly when it suddenly produces a reading nobody can explain. What has really caught researchers' attention is the shape of the anomaly itself. When plotted against time, the spike forms an almost perfectly symmetrical curve, rising and falling at matching rates, something rarely seen in natural magnetic field data at this distance from any star. Natural cosmic phenomena tend to be messy, asymmetrical, shaped by chaotic processes that leave irregular fingerprints. A clean, mirrored spike like this one is the kind of shape you would expect from something with a defined boundary, a discrete event with an actual beginning and end, rather than the diffuse, drifting behavior interstellar space usually produces. This isn't the first time one of the Voyager probes has produced a reading that briefly confused the people monitoring it, and looking at that history helps put the current anomaly in perspective. Voyager 2, Voyager 1's twin, launched just weeks earlier in 1977, and the two spacecraft have occasionally recorded strange, hard-to-explain fluctuations within days of each other over the decades, usually tied to the complex, turbulent physics of the heliopause boundary they both eventually crossed. Most of those past anomalies were eventually explained through careful, patient analysis, often taking months to fully resolve. Engineers monitoring Voyager 1's current anomaly have reportedly begun checking Voyager 2's most recent telemetry as well, looking for any trace of a similar 6-minute disturbance that might suggest both spacecraft encountered the same interstellar feature from different positions in space. There's also the matter of what Voyager 1's engineering team has been focused on for the past few weeks, well before this anomaly ever surfaced, and understanding that context changes how the discovery timeline reads. In April, engineers deliberately shut down the low-energy charged particles instrument, specifically to conserve power for future operations, a sacrifice made as part of a broader effort NASA has nicknamed the Big Bang Fix internally, an attempt to extend the spacecraft's working life using a set of carefully sequenced power adjustments. That same fix had already been successfully tested on Voyager 2 earlier this year, and engineers were preparing to attempt the identical maneuver on Voyager 1 this coming July when the magnetic anomaly first surfaced. The timing means researchers were already combing through Voyager 1's instrument data with unusually close attention, checking every reading in preparation for the upcoming procedure, which is very likely the only reason the anomaly was caught as quickly as it was. NASA's Jet Propulsion Laboratory has confirmed the anomaly is real and currently under review, while carefully avoiding speculation about its cause. In a brief statement, mission personnel described the reading as unexpected and said the team is working to rule out instrument degradation before considering other explanations. That caution is reasonable, and it deserves to be taken seriously. Voyager 1's instruments are nearly 50 years old, operating at temperatures and radiation levels far beyond anything they were originally designed for, and aging electronics can absolutely produce readings that look meaningful but are really just the slow decay of components never meant to last this long. But there's a detail that complicates the instrument failure explanation considerably. Voyager 1's plasma wave subsystem, an entirely separate instrument measuring different physical phenomena through different hardware, registered a small but measurable disturbance at almost exactly the same 6-minute window. Two independent instruments, built with different components, measuring completely different physical properties, both showing something unusual at nearly the same moment, is a much harder coincidence to explain away as a single failing sensor. If one instrument had degraded and started producing noise, you would not expect an unrelated instrument on the other side of the spacecraft to register anything at all. Some scientists outside the immediate mission team have offered grounded, physics-based explanations worth taking seriously. Interstellar space is not empty in the way most people imagine. It contains thin plasma, cosmic rays, and occasionally the leftover shock waves of ancient supernovae that rippled outward long before Voyager 1 ever launched. It's possible, these researchers argue, that Voyager 1 simply passed through a small, previously uncharted pocket of disturbed plasma, a kind of interstellar eddy left over from some ancient stellar event, producing a brief, unusual reading that looks stranger than it actually is. This remains one of the more plausible natural explanations, and any honest account of this story needs to include it clearly. Still, there are reasons researchers aren't fully satisfied with that explanation either. Any plasma disturbance capable of affecting both a magnetometer and a plasma wave instrument simultaneously should, according to existing models, leave some trace in the surrounding density readings as well. Voyager 1's plasma density measurements from the same window show almost no change at all, a mismatch that doesn't fit cleanly with the ancient shockwave theory the way scientists initially hoped it might. Whatever passed by or through, Voyager 1 during those 6 minutes did not behave exactly the way an ordinary plasma disturbance should. There's also the matter of direction. Using the limited directional data available from Voyager 1's aging sensors, engineers attempted to estimate where the anomaly originated relative to the spacecraft's position. Early analysis suggests the disturbance did not come from directly ahead, in the spacecraft's line of travel, or from behind, where you might expect an effect trailing from the heliosphere. Instead, it appears to have arrived from an angle roughly perpendicular to Voyager 1's flight path, a direction that doesn't correspond neatly to any previously mapped feature of the local interstellar medium. It is, in the words of one researcher familiar with the analysis, coming from a part of the sky Voyager 1's team simply wasn't looking at. This is where the story shifts from a scientific curiosity into something that has genuinely unsettled a handful of people inside the mission. Voyager 1's original golden record, the same kind carried by its twin, was designed as a message meant to survive for at least 1 billion years, a deliberate act of communication aimed at absolutely no one in particular, and yet everyone at once. Carl Sagan and the team who assembled it chose sounds and images meant to represent the full breadth of human experience. Greetings in dozens of languages, music spanning cultures and centuries, diagrams intended to convey humanity's location in the galaxy to anyone capable of decoding them. For nearly 50 years, sending that message has been a one-way act, a whisper released into darkness with no expectation of reply, and no serious scientist working on the mission ever genuinely planned around the possibility of one. An unexplained, structured disturbance arriving from an unmapped direction, registering across multiple independent instruments almost simultaneously, is the first time in the mission's history that anything has looked even remotely like an answer, even if every cautious voice on the team is quick to point out how far that framing outpaces the actual evidence. To be absolutely clear, nobody at NASA, and no credible researcher studying this data, is claiming Voyager 1 has made contact with anything intelligent. That leap is not supported by the evidence currently available, and responsible coverage of this story has to say so plainly rather than let the mystery run further than the data actually justifies. What the evidence does support is narrower, but still remarkable in its own right, an unexplained magnetic and plasma anomaly, confirmed across separate instruments, arriving from a direction nobody expected, at a spacecraft that has otherwise behaved with almost boring consistency for nearly 5 decades. There is a deeper irony sitting underneath all of this that's worth pausing on. Just weeks before this anomaly surfaced, engineers deliberately shut down one of Voyager 1's remaining instruments, the low-energy charged particles experiment, specifically to conserve power and buy time for future operations. If that instrument had still been running, it might have provided an entirely separate data stream capturing the same event from yet another angle, potentially settling the debate over natural explanation versus something stranger within days. Instead, that window closed permanently in April, and the mystery is now being pieced together using only the instruments NASA had the foresight, or the luck, to leave switched on. Compounding the difficulty, Voyager 1's spectacular distance from Earth makes rapid investigation almost impossible by ordinary standards. Every single command sent to the spacecraft takes nearly a full day to arrive, and any resulting data takes another full day to make its way back. A follow-up instruction asking Voyager 1 to reorient slightly or adjust. Its sensitivity to better capture a repeat of the anomaly would require nearly 2 days round trip just to learn whether it worked at all. In an era where most scientific instruments deliver near-instant feedback, Voyager 1 forces its own investigators to wait, quite literally, at the pace of light itself. NASA's official position remains cautious, and appropriately so. In public statements, the agency has emphasized that Voyager 1 continues to operate normally overall, and that the anomaly, while genuinely unusual, does not indicate any malfunction threatening the spacecraft's continued survival. Engineers have stressed that ruling out instrument degradation remains the top priority before any other explanation is seriously entertained, a methodical, unglamorous process that could take weeks or months to complete properly. That is, by every measure, the correct and responsible way to handle a genuine anomaly, and it stands in sharp contrast to the more sensational theories already spreading across parts of the internet. And yet, even inside that cautious, methodical process, something has clearly shifted. Multiple instruments, independently built, independently calibrated, registering something unusual at nearly the same 6-minute window, arriving from a direction nobody had flagged as significant, is not the kind of event NASA typically calls simply routine. The agency's own choice of words, describing the reading as unexpected rather than explained, tells you plenty about where their internal confidence currently sits. What makes this moment feel especially significant is where it falls in Voyager 1's timeline. The spacecraft is approaching the twilight of its operational life, a fact NASA has been remarkably open about for years now. Every instrument still functioning represents a hard-fought victory against a power budget that shrinks a little further every single year, and every new reading carries the weight of possibly being one of the last meaningful data points this particular machine will ever send home. If Voyager 1 was always going to encounter something strange during its long journey outward, the fact that it happened, now, in the twilight of its working life, on the edge of a historic light day milestone, adds a kind of narrative weight that even the most cautious scientists have quietly acknowledged feels unusual. Later this year, on November 15th, Voyager 1 is set to reach a distance of 25.9 billion kilometers from Earth, officially becoming the first human-made object to sit a full light day away from the world that built it. NASA has been counting down toward that milestone publicly for months, framing it as a celebration of just how far human ingenuity has managed to travel, using little more than 1970s engineering and an extraordinary amount of careful planning. That celebration is still very much on schedule, but it now arrives alongside an open question nobody expected to be asking this close to such a historic date. Whether the emptiness Voyager 1 has been traveling through for decades is quite as empty as everyone assumed. There is also the simple, almost overwhelming scale of what Voyager 1 represents that's easy to lose sight of amid the technical details. It is a machine built using 1970s technology, carrying less computing power than a modern wristwatch, traveling through a region of space so remote that sunlight from our own star is barely a distant memory by the time it reaches the spacecraft. It has already outlived every original prediction for its lifespan by decades, and it continues to return data from a part of the universe humanity has never directly sampled before. That a machine this old, this far away, and this quietly resilient could still produce a reading nobody fully understands says as much about the strangeness of interstellar space itself as it does about anything specific that may have happened during those 6 minutes. It's worth remembering, too, just how much patience this entire investigation demands from everyone involved. Every follow-up question, every request for a spacecraft maneuver, every attempt to gather more data to explain the anomaly has to survive an almost 2-day round trip through the void before anyone on Earth even knows whether it worked. That kind of glacial back and forth would be unthinkable for almost any other scientific instrument operating today, and yet it has been the operating reality of the Voyager mission for nearly half a century. Whatever Voyager 1 encountered during those 6 minutes, humanity is now investigating it at the slowest possible pace physics allows, one 23-hour transmission at a time. For now, the investigation continues quietly, methodically, and without the kind of dramatic conclusion that headlines often promise but rarely deliver. NASA has indicated that further analysis, including cross-referencing the anomaly against archived data from ground-based observatories and other deep space missions, is ongoing. Whether the eventual explanation turns out to be a previously uncharted pocket of ancient plasma, an aging instrument finally showing its decades of wear, or something that genuinely expands what we understand about the boundary between our solar system and the wider galaxy, one thing remains true regardless of the outcome. A machine humanity built and then let go nearly 50 years ago just returned a piece of data from the edge of known space that even the people who have spent their entire career studying it cannot yet fully explain. Make sure you're subscribed and notifications are turned on, because NASA has indicated a fuller analysis could be released within weeks. And whatever answer eventually comes back from 25 billion kilometers away is going to take almost a full day just to reach us after they send it. Until then, Voyager 1 keeps moving outward, carrying humanity's oldest still-running conversation with the universe. And for the first time in nearly 50 years, that conversation might not be entirely one-sided anymore. Whatever the final explanation turns out to be, ordinary or extraordinary, this is a story worth watching closely, and we'll be here the moment NASA says more.